All right, this is a continuation of PCA, and you should switch over from PCA 1 lecture notes to PCA 2 lecture notes because I'm going to be covering those notes for this video and perhaps another video if necessary. I want to try to keep these a little bit shorter than the previous ones. So there are two parts to this lecture. The first part is reviewing Dunteman. It's going to be very brief. Even though the lecture note says I'm going to cover it in 40 minutes, I'm not going to take 40 minutes to cover this in the video. I'd rather you read over Dunteman and then see the points that I highlight, which is far more important than just listening to me reiterate what Dunteman had already written. So the objectives of this section are threefold. One is I want to tell you a little bit more about the details of PCA applications, and then go through the interpretation of PCA results, and then finally discuss Dunteman examples and the major points that he brings up. So there's three applications, PCA applications, and they're not necessarily mutually exclusive, but they do fall under some very simple applications and processes that you'll find PCA to be quite useful for. So the first one is instrument scoring or scaling. So you can take an instrument, and in my example, I give an instrument of a 7-question instrument to assess your preferences for course material. And the 7 questions are outlined in the notes, and what I give all the class is these 7 questions, and I say, please rate on a scale of 0 to 3 how interested you are, 0 meaning not interested, and 3 meaning totally excited. And when I run the PCA, I find that I get roughly 3 principal components that can be extracted that account for a sufficient amount of variance in the original variables. And then what I do is I walk through the A weights and how the A weights are used with the standardized scores in order to create scores, principal component scores. I also show you what the eigenvalue cutoff of 1 is, and that's I refer to that as the Kaiser criterion. The Kaiser criterion is the criterion by which you would select or deselect individual items or variables based upon their performance. I recommend that you not stick closely to these cutoffs because these cutoffs oftentimes will get you into trouble. They get you into trouble because, hold on a second, I just want to, okay. They get you into trouble because they primarily they mask what people really don't understand, and what they don't understand is oftentimes why the Kaiser criterion would ever be developed. So let me just give you a rationale for the Kaiser criterion, and that way you can interpret some of these results. But then I trust that you won't use the criterion as a rule, but more as a guideline. So remember that we start out with n number of principal components from n number of variables. And what we want to make sure is that the end result is actually an efficient result. So we start out with a certain number of variables, and the variables that we derive or we combine together to create these components ought to be better than the original variable. So what do I mean by that? Well, remember that principal components revolves around variance. It's focused on maximizing the variance of the principal component from the original variables. So in this case, we have 7 variables. We have 7 variables that are standardized, and because they're standardized, they all have a variance of 1. And so the total variance available to us from the principal component model is 7. And ideally, what we would like is a principal component to reproduce, or to be able to reproduce, variance that's the equivalent of 1 of the original variables. So that's why variance greater than 1 means that that principal component will reproduce the variance of at least 1 variable. And you'll see that on the 4th page of my notes, where there's a scree plot with eigenvalue cutoff that goes straight across. All right, now that's a Kaiser criterion. Now often there are reasons why we may skip, or we may have a higher threshold or maybe even a lower threshold. And what I recommend that you do is select the threshold but be able to defend it. So in this case, what I did is I selected only 3 principal components from possible 4, because 4 of them satisfied the Kaiser criterion. Why I did that, I'm not entirely sure. I just wanted to show that you can indeed violate these rules. And sometimes it would be just for interpretation's sake. Maybe it's for simplicity. You want a more parsimonious model, but whatever. There are a variety of reasons in which you may want to change what the cutoff is. At least you should know what the Kaiser criterion is. So I chose 3 principal components, and then I walk you through how each one of these principal components, the A weights from the principal components, can be used to calculate principal component scores. So principal component scores are the actual new variables that get inserted into your data set if you want them. In SPSS, I think it does it by default, or maybe it doesn't. There's a checkbox to save the variables. And in R, you can just merge them. You can save the scores and then merge them in with your original data frame. So in this case, what I do is I just walk you through exactly what I'm talking about in terms of A weights, standardized variables, and you'll see in my tables, I create these tables where I have PC1 weights, the response weights that are all standardized. So this is just for the first subject. And then I compute a product, which is the weight, the A weight times the X. Remember, the X is a standardized vector for each subject. What I'm doing is I'm calculating the principal component scores for the first subject, but only for first principal component, okay? And then I talk a little bit about, after that, about principal components. Remember, they're orthogonal, and the reason why they're orthogonal is that they're computed hierarchically. So once you get your first principal component, you residualize out that first principal component from the original variables. So each original variable will be predicted by the principal component, and then we'll save the residuals. Now, fortunately, we don't have to do that because PCA procedures do this for you automatically. And then I walk you through exactly how the second principal component score is calculated for the first person. So I go through this whole listing just to calculate 2 scores. And what I'm trying to show you is 2 things. One is you can use it for instrument scoring, but 2, I'm trying to reiterate and really reinforce the idea that principal components are orthogonal because they're calculated, these scores are calculated hierarchically. The next thing we can do in terms of principal component applications is model simplification. So we can take a variety of variables and we can simplify them. And I showed you that in the crime data set and the crime example in the previous lecture notes. That by simplifying, we can oftentimes create models that really are more useful for us because we can take multiple dependent variables and collapse them into single variables that are now more useful in multiple regression and correlation or in ANOVA models. And then finally, another example that I brought up before was multicollinearity. Now, all 3 of these examples are really trying to pull together the same concepts. And that is, one, that there's orthogonality to our principal components. So if you have predictors, we can use this for model simplification, but we can also use it to eliminate some of the problems in MRC, namely multicollinearity. So if we have multiple predictors of an outcome that are all correlated, the best thing that we can do sometimes is to eliminate multicollinearity by finding that shared variance. Okay, the shared variance among our predictors, and then grouping that together, clustering it using a principal component model. And the nice part about PCA is PCA always produces independent principal components. So now we can use, instead of, let's say we have 3 predictors, or in my example here, starting on page 8 of the PCA notes, is I take 2 predictors that are highly collinear, and I reduce them to 2 principal components because I have 2 predictors, 2 principal components, and I show through various machinations of this example, and also a little bit of a tangent where I talk about variance inflation factors, something that you should know about. And why should you know about them? Because variance inflation is an indicator, or is one of the tools that we use for multicollinearity. So it'd be helpful for you to at least review that material. And if you don't know much about it, read my notes and then read online. There's plenty of material online about variance inflation factors. So I show from my two predictors how I can reduce collinearity, in fact, eliminate it by definition. And then what I do is I use those two principal components as predictors, and you'll see that the first principal component accounts for almost 80% of the variance, even though the variance is less than 1. Now, the interesting part about that is, remember, we start out with 2 variables, so the variance for that's available is 2, and we barely scratch the surface of being able to do much more than reproduce less than a 1 for the eigenvalues. So for the variance, that's a great example of where we want to abandon the Kaiser criterion. Kaiser criterion will get you into trouble. Or maybe in this case, the Kaiser criterion would actually tell you that there is no good solution. It's okay. We used the tool for what it was useful for. We combined our 2 predictors. By combining our 2 predictors, we eliminated multicollinearity. Okay, now, so according to Dunteman, there's a whole bunch of applications that we can use PCA for: selection of subsetting variables. I tend not to like that because that's more of an empirically driven procedure rather than a theoretically driven procedure. And you'll hear from me a lot is that I think theory should trump the data. Paul Dirac used to say, he's a physicist, was a physicist, said that never let data ruin a perfectly good theory. Well, I think sometimes we, in psychology, we lack the theory, or we have great theories, but we let data dictate what we're doing too much. So be careful about using these empirical approaches for selecting relevant variables. I've shown you that it's a good adjunct to MRC, to multiple regression and correlation. And the way it's useful is it helps us eliminate multicollinearity. It is a tool for detecting outliers, but there are far more sophisticated and also more detailed tools about that, and we'll talk about that later when you look at Cook's distance and things like that when we're doing exploratory data analysis. It can be used to aid classification of individuals, but again, there are more sophisticated tools nowadays than PCA. I wouldn't rely on PCA for that. And then the other thing is you can use it to identify clusters of predictors. Again, that's more of clusters of predictors that might be useful for improving your predictive models. Again, I think that's a little bit too empirically driven. That's just my taste. You're certainly welcome to have your own preferences for that. Okay, finally, the last 3 points. PCA at its roots is data reduction. Remember, that's what we're talking about in these first 2 segments of the class. Talking about PCA and EFA, they're both data reduction strategies. Take many variables, squeeze them down to fewer. The results of PCA relies on the data analyst to make decisions. Yes, and we've already talked about one of those, and that is how many principal components to retain. And one of them could be, you could use a heuristic like the Kaiser criterion, but you can use a lot more. And again, there are merely heuristics to guide our use of PCA. So this is the principled application that I talked about in the first day of class. All right, now finally, I want to go over a few important topics or points about PCA not covered in Dunteman. All right, and that is, first, there are a bunch of tests. There are tests for PCA assumptions. Remember, I talked about these before: linearity, normality, sphericity, and reliability. I'm not going to go over them again. Test of linearity, best thing to do is graphically plot your results. And you can do that with matrix scatter plots. I think that that's fairly easy and straightforward to do in SPSS, and certainly in R. You just plot your data frame. Tests of normality, there are both numerical tests, Kaiser, the Kolmogorov-Smirnov test, and Shapiro-Wilks test. These are two of many empirical tests for normality, but I tend to prefer not single numbers, but rather graphical depictions of normality. So I use QQ norm plots. They're fairly easy to produce. I'd recommend them. Okay, again, linearity or rectilinearity among our variables, plot. Normality, I prefer to plot. You may prefer something else. Tests of sphericity, again, with PCA, we don't really have to worry about that too much because all our variables are standardized. So equivalence of variance is really ensured by the pre-treatment of our variables. So I wouldn't worry too much about that. Bartlett's test is one that's common. It's commonly produced in SPSS. I think there's a function in R that you can use. I'm not that fond of Bartlett's test, but you may find it useful. I recommend that you ignore people who give you heuristics for interpreting Bartlett's test because they're not that good, okay? Finally, tests of reliability. Well, actually not finally. I got two more things I want to talk about. Tests of reliability, remember I said in terms of the assumptions, PCA mandates that our data are reliable. That have a reliability of 1.0. And we know that that's a convenient fiction. So one of the things that I recommend is that you at least address it and you at least think about it. Now remember, reliability is a double-edged sword. If you go down that path of somehow or another denigrating PCA, you have to hold that same argument against multiple regression and correlation, which mandates the same thing. Instead, I'd rather you be thoughtful about what reliability means in terms of the model, and are your data really reliable? Are your variables as reliable as possible? Now you can assess reliability to a degree. You can assess internal consistency. You can assess test retest. Oftentimes, though, that goes way beyond the data that you have available to you. Nevertheless, it's not a bad thing to check it out, because if you have horrible data, your poor data is really going to attenuate any of the correlations, and therefore it's going to make it much more difficult to interpret the results. Okay, finally, and this is finally, the SPSS produces a statistic called the Kaiser-Meyer-Olkin statistic, or KMO, and this tends to be an overly interpreted test. And let me just give you the reason for it. You can read my my bit on it. It starts at the bottom of page 11 in the notes. But the KMO statistic is one that is derived by essentially how interpretable are your results. Okay, and it assesses the correlation matrix ahead of time. I think as data analysts, most of us already understand how interpretable our results are simply by looking at the results and then knowing the data. Using indices like KMO to tell us whether our data and our results from these data reduction procedures are likely to be interpretable is sort of like asking whether the car is going to start when you're in a running car, okay? Or if the car doesn't start. So I'd recommend you not rely too heavily on these statistics, rather look at the data. Now, granted, in my class, for examples that I give you for modules, the data are not going to be interpretable. You won't know what the variables mean because I made them up. If you really want, you can assign names to them and give them meaning. That's great. At the same time, I recommend you not do that during the module because it just takes up time. But nevertheless, I fully recommend that you look over my notes, especially for this KMO and Bartlett's test, because these are the two pitfalls for most SPSS users. SPSS churns out lots of output. And if you have all this output that you can't interpret, that's a problem, okay? So make sure that any output that you have generated, you know about. And also be sure to generate as much output as you can to really understand what the model is and to be able to explain it. Okay, so this concludes PCA for now, and don't worry about it. I'm coming back to communalities and all sorts of things that are relevant to both PCA and EFA. It's just that in EFA, sometimes by comparing the two procedures, you really have a much better understanding of both of them. All right, so stay tuned. EFA begins.